last mechanism to defend us against disease is specific immunity, or our adaptive defenses, or our third line of defense. Now, this is going to kick in when everything else was insufficient in keeping the organism at bay, and the organism has gotten systemic. So it is not restricted to the initial infection site. And with specific immunity, we are hunting down individual antigens for destruction. We're not just blanketly killing off everything. Each T and B cell is looking for a specific antigen to which it bears the either T cell or B cell receptor. And so it recognizes and is directed against particular antigens. And lastly, specific immunity has memory. Once an antigen has been detected and an immune response has been mounted against it, if everything works the way it's supposed to, and notice I say if it works the way it's supposed to, then we will remember that antigenic structure for later, and once we encounter that antigen again, then we mount a stronger and quicker second attack. And many times, most of the time, when we're affected again, we don't even know, because we have already killed off the organisms before they've become virulent enough, or that they have grown in large enough numbers to cause disease to happen, for us to be aware that we are ill. All right, so this shows where the lymphocytes come from. So it is the lymphocytes, the B lymphocytes and T lymphocytes, that are involved in specific immunity. And they are going to be produced in what we call the primary lymphoid organ of the bone marrow, and then they will mature either in the thymus or they'll remain in the bone marrow. So all blood cells, remember, all blood cells are produced by the hematopoietic stem cells that we find within the bone marrow. And so both T and B lymphocytes will be made, and they'll be their precursors. They'll originate in the red bone marrow. Then the cells that are to become T cells will migrate to the thymus, and they will mature there. And we'll talk about, well, what does it mean to mature? And then the B cells will mature in the bone marrow, and they'll remain there. Now, when the cells leave, if you notice what these lymphocytes look like, they're just little cells with nothing on the outside, no cell receptors on the outside. And so that's what happens to them while they're in the thymus and the red bone marrow. During maturation, the lymphocytes will develop their immunocompetence, and more importantly, maybe self-tolerance. So let's talk about what immunocompetence is. So in order to fight off an infection, you need to have a receptor for a particular antigen. And let's just go back, because that's one of the questions, is what is an antigen? And so an antigen is typically a protein that we find on the surface of a cell, and one that is going to trigger an immune response. And that's what antigen means. It's an antibody former. So antigen means antibodies are formed from the presence of this structure. They're going to be made by the body, or they're going to be made by the cell itself. So whatever that cell happens to be, whether it's a Staph aureus or a streptococcal organism, if it's a malarial organism, if it's a HIV, whatever. So there's stuff on the outside that our body has the ability to recognize as foreign. And each one of our T and B lymphocytes produces a T or B cell receptor for that particular antigen. And so what the T cells and B cells are doing in the bone marrow and the thymus is learning what receptor they are going to make, and then make that receptor on all of their clones. And so, well, there aren't any clones, on themselves. So each B and T cell has a receptor for a specific antigen, and it can only bind to that antigen. And so let's say if we have a T cell for Staph aureus, for example, well, we're not going to. If we have a B cell for Staph aureus and a streptococcal bacterium goes by, it won't even give it a second glance because it doesn't have the receptor to it. But then somewhere else in your body, you're going to have the B cell that will have the receptor for that streptococcal organism, and then it will fight off that streptococcal organism. So B's and T cells are very, very focused in what they kill. They target only one antigen. Out of the 100 million antigens there can be out there, yeah, we have that much variability in our T and B cells. 100 million T and B cells that could have the ability to attack and eliminate every possible antigen that's out there in the world. Now, self-tolerance. Here's the thing. We do not want to attack and destroy our own body tissues. And so we have to recognize what antigens belong to us. And you probably are familiar with when a person needs a tissue transplant, we try to find a match for them. Well, what are we matching? Well, we're trying to match up what antigens that they have on their kidneys or their hearts or their livers or whatever tissue that they're receiving, that we want to have an antigen as close as possible to what we have in our bodies. And even when we find a match, it's still not perfect because we don't have a identical twin, every one of us. That's the only person that would have the same antigenic structure as we do, is our identical twin that bears the same genome. But we've tried to find a match, and so when we find someone that's close, then we still have to take immunosuppressive medications for the rest of our lives, because our immune system could kick in and start destroying that that transplant. Now, here's another one. What about autoimmune diseases? Well, that's the same thing, is that with an autoimmune disease, our bodies are not tolerant to self and identify self as foreign and start to attack that and destroy that. And I don't think that you have to know about autoimmunity. Well, there's a little bit of autoimmunity. So we'll get to that again in the autoimmune section. All right, so we've learned self-tolerance. We go, okay, I recognize those self-antigens, so I'm not going to fight them off. And how does that happen? The cells that might bind to our self-antigens will carry out apoptosis. They will program cell death. So those cells are destroyed in the thymus and never to exist again. So it's quite the process that happens within the thymus. It's very important. And this process happens until we get into our early young adult years. And by that time, we do not do any more maturation with our thymus. We don't use it anymore. And so it then shrivels up. It just atrophies until it becomes connective tissue, basically, and we can't even see it. I've never seen a thymus in an adult cadaver that I've dissected or that I've seen in my lifetime. However, I have seen in fetal cadavers, I have seen thymuses, and they're very distinct and they're very well formed because you just use it up through adolescence and then you don't use it anymore. Okay. So moving on, what happens to the cells that then make it through that education self-tolerance program process that leave the thymus and leave the red bone marrow? Well, now they're going to go throughout your whole body. And so what they have to do is encounter an antigen. So the T and B cells are going to travel both through the lymph and through the blood and pass into and out of the tissues, and they are just going to constantly cycle for the rest of your life through the bloodstream and the lymphatics. Now, if we encounter an antigen in the lymphatics, super, because we have little places that we want to find them, and that's where they're going to be first anyway. Because remember, our lymphatic system is what drains our interstitial fluid. And where's our interstitial fluid? Out in our tissues. And where does infection happen? Out in our tissues. And so we want to try to stop infection from spreading beyond the lymphatics. But remember, those lymph vessels end up back into the subclavian veins and back into circulation. So we do immunosurveillance through the bloodstream and the spleen. but there are not many way stations in order to discover the antigen, to be able to mount a response, to have an antigen challenge. And so we rely on the lymph nodes, and the macrophages bringing the lymph nodes bringing the antigen to the lymph nodes in order for the T's and B cells to find them. So if you remember the structure of a lymph node, there were germinal centers and the medulla and the cortex where the T's and B cells are hanging out waiting for the macrophages to come, and then they take a look at what the macrophages have to present. And in fact, macrophages are known as antigen presenting cells. B cells can also be antigen presenting cells, and so what they're going to do is take the antigen to the T helper cell. And in essence, the T helper cell will take a look at the antigen, make sure that it's not a self-antigen, and then they just go ahead and kill it off. And then they secrete, and then the T helper cells will secrete cytokines like interleukin 2, interleukin 1, and that will stimulate the production of cytotoxic T cells from a clone, which I'll get to in a minute, and the B cells from their clones. Okay, so notice they're immunocompetent but naive because they have not met their antigen yet. Okay, so the immunocompetent means they have B and T cell receptors on the outside, but they haven't met anybody yet. If we take a look at this B cell right here, notice that there are little antibodies, Ys, stuck here on the outside. So those are the B cell receptors, and they will bind to the antigen. As you can see, the arms of the antibody will bind to the antigen, and then they can take it to the T helper cell, or the macrophage may engulf it, and then they put the antigen on the surface of the macrophage, and then they go to the helper T cell in a lymph node and say, does anybody recognize this? And then, one of the T helper cells raises his hand and says, yeah, I know that one, and then boom, it's D-Day, and they just go and try to kill it off. All right, so antigen challenge is going to happen typically within a lymph node. The T's and B cells do not sit in the lymph node for your whole life. They sit there for a while, and then they'll go somewhere else, and they'll try to find. And that's why it takes 7 to 10 days once you've been infected for you to start getting better, because you got to find the antigen, and then you got to mount a response against it. And what has the antigen been doing in that 7 to 10 day time period? Well, they've been building an army themselves. So we're playing catch up. By the time we find it, we've already, that organism has already invaded us systemically, and so now we got to go around and fight everybody. But when we find it, then we go crazy, and we do this thing called proliferation and differentiation, or we go through clonal selection and clonal expansion. So clonal selection is when this little B cell right here finds this antigen, this extracellular antigen, and goes, cool, I bind to that, so I better start killing it. So now we've selected, the antigen has picked which B cell is going to kill it off, which is kind of interesting. And then this one B cell, because that's the only one you have that's going to bind to these antigens, is then going to go through what we call clonal expansion. And so notice that it's going to make a whole bunch of copies of itself. Now, B cells, when they go through clonal expansion, make a whole bunch of these kind of cells that don't look much like the original B cell because they don't have to, and these are called plasma cells, and I'll get into plasma cells in a minute. And the B cell will also make a set of memory cells, which will look just like the original, and I'll get into that in just a minute too. So activated lymphocytes, so these that have been gone through clonal selection, will proliferate or multiply, which will then go through clonal expansion and differentiate into the effector cells. So that would be these plasma cells right here, and memory cells. Memory cells and effector T cells, as well as B cells, I don't know why they just put T cells, circulate continuously in the blood and lymph and throughout secondary lymphoid organs. Okay. All right, so let's talk about humoral immunity, or antibody-mediated immunity. So this is what the B cells do. The ones that came from the bone marrow. That's why we call them B cells, but not really, because they were actually found in birds in a thing called the bursa of fabricus, and that's where they got B from. But T cells came from the thymus, and so that's where they got their name from. All right, so B lymphocytes mature in the bone marrow, proliferate in the lymph nodes and spleen. So that's where they're going to divide and divide and divide. Once they've been clonally selected, then they'll go through clonal expansion. And so what does that? When they are activated by antigens binding to their B cell receptors. Okay, B cell receptor. The B cell with the receptor for a specific antigen will then grow and rapidly divide, producing a family of cells with the exact same antigen-specific surface receptors called a clone. Okay, so they'll make a whole bunch of memory cells, but then the plasma cells, however, do not need to recognize the antigen anymore. They just know they turn into antibody factories. And so they will make, so the antibodies that they secrete will be exactly the same as those antibodies that were present on this original B cell, on the parent cell. So the clone cells that don't differentiate into plasma cells become the memory cells that will have the same surface receptors as the original B cell. And the memory cells are the spies. And so they're not going to fight in this first infection. So this primary infection that we have, now that they've been activated, they're going to go off and they're going to go and do their own thing. And then when we're infected again, boom, now I got a whole bunch of B cells that have the ability to attack and destroy that and turn into even more plasma cells. And so let's look at that process. So here in the primary response, here's the antigen that is going to pick the antibody that bears its receptor. And so these two B cells are going to fight somebody else, but this one in the center is going to fight off this antigen. So now we're going to produce a clone. And then they're going to differentiate into plasma cells, which essentially, well, we can call them effector B cells, but essentially they are antibody factories. And then we also produce some memory cells. So these guys are going to be involved in the first infection, and they're going to secrete their antibodies. And this will be sufficient to get you better. But the secondary response can be years later, and here comes that antigen again. But now the memory cell found it really fast, and multiple memory cells found them. And so now they're going to produce even more plasma cells with even more antibody and produce another batch of memory cells again and again and again. And so every time we're infected with that particular antigen, our response against that gets stronger and stronger and stronger. And so a lot of times we will never ever know that we've been infected because we've been infected so many times. We've got so many memory cells and the capacity to produce so many plasma cells that we just wipe it out in an instant. That is why we vaccinate. So when we are presented, and I know vaccination doesn't come right now, but this is why we do it. So what we want to do is introduce a non-lethal, a non-pathogenic antigen to our bodies. So we're going to give us an antigen that is not pathogenic, does not have the ability to cause disease. So then it's going to pick our B cell, and then the B cell will go through this process, and I'll make a whole bunch of antibodies. So I've got antibodies stored in my body, waiting in case I might be present with the polio virus, okay? And then a whole bunch of memory cells. So I'm going to do that once, and then I'm going to do it again, and then I'm going to do it again. And most vaccines require 3 booster shots. Some require 4 as our normal regimen of vaccinations, or our schedule of vaccinations. So what have we done? We've done this process 3 more times. So we did this one, and then we did this one, and we did this one, and we did this one. And so what we did every time was make our immune system stronger and stronger and stronger. And so just because we got immunized once against something doesn't mean that we're going to be sufficiently defended against that particular pathogen. So we want to make sure we finish our full course of vaccinations, that we get all the booster shots that we need to have. And so that's what vaccination is. And well, I'll get into that in a little bit. Okay, so here's what happens. We're exposed to antigen A. We produced enough antibodies to fight it off. Boom, we get better by day 28. And then we're infected with it again. Well, now look at how much more of a response we get and how much more rapidly we get that response. Because here it took us 5 days. We were exposed on day 0, so 5 days later we started measurable antibody production. But then here on the day 20, so here's day 1, day 2, boom! Okay, we didn't even wait or nothing. We just started producing antibodies right away. And, you know, what are we? 1,000 times more than what we made the first time. So it's a much more rapid and a stronger response. And then our antibody titer will stay up there too, and will keep us for weeks and weeks from getting infected. Here, though, is a second antigen. This is a different antigen, not the same one we got infected against. And boom, we got to go through the exact same thing again. So these two are two different primary responses. This second one is the secondary response to the same antigen. Okay. All right, yeah, I guess that's it. Okay, so what makes B cells effective is the fact that they can produce antibodies. Now I gotta tell you right from the outset, antibodies don't kill a thing. Antibodies are just markers. Antibodies will stick to the outside of an extracellular pathogen, so whether it's a bacterium or a free-floating virus or a fungus or some kind of parasite, but not already infected in a body cell. That's the role of the T cells. But if you got something free out there in your lymph or your bloodstream, antibodies are going to stick to it. And once they stick, then we'll get into what happens after they stick. So antibodies are Y-shaped molecules. They're made of 4 polypeptide chains, 2 heavy and 2 light. They're going to be bound together in a particular Y-shaped structure with disulfide bonds. The 2 heavy chains and the 2 light chains each have a variable region, which is on the arms, or we call them the FAB region, and then we have a constant region, which is the stem or the FC region, and the FAB region of the antibody is what binds to a specific antigen. So if we take a look at this picture, here is the heavy chain bound in these little domains with disulfide bonds and bonded to one another with disulfide bonds. Then we have the light chains out here also being bound to these heavy chains, and then these little loopy domains on the stem region will also have receptors for macrophages, so that they can act as opsonins, and then they'll also have a little receptor for complement in order to trigger complement activation. So every antibody in the whole entire world is this lighter blue and purple area. Every antibody looks exactly like this in the whole entire universe. But it's out here in the darker regions where we have variability. So every antibody in the whole, every type of antibody that we have bound on the surface of every different B cell is going to be different. So I can have 100 million different combinations, different shapes out here in my FAB region that has the ability to bind to every possible antigen that could ever be out there in the world, which is amazing. Okay, so here is what's going to happen when antibodies engage an antigen. So they're going to cause an antibody-antigen complex. But there are 4 things that happen. These two actually go together in a thing, in a category, but you can remember them by the acronym PLAN, P-L-A-N. So P stands for phagocytosis due to opsonization. And we'll take a look at the picture in a minute. So remember, sticking to the outside of a bacterium allows a macrophage to eat it. And that process is called sticking, is opsonization, and eating it, of course, is phagocytosis. The second thing is lysis, and remember, complement will produce once activated, will produce a membrane attack complex, and then that will cause lysis of the bacterium. So there's lysis. The A stands for agglutination. So agglutination, remember with blood typing, is when antibodies are going to bind to the antigens that are on the surface of the red blood cells, and I'll show you why they agglutinate, why they like to clump together in a minute. They'll also stick to soluble antigens. Remember, things that are floating around in the plasma that aren't bound to anything. And they'll stick to them and make them come out of solution, and then the macrophages can eat them. So that's the A. So far we have P for phagocytosis, opsonization, that mediates phagocytosis. Then we have lysis, so the activation of complement to produce lysis. Then we have agglutination. And then the last one is, again, why we vaccinate is neutralization. And so what we're trying to do is neutralize viruses, keep them from infecting in the first place. So let's say I do have a vaccine for polio. So now I present that polio antigen to my body, and then because I'm just sending them the antigen. So now my B cells, because it's not going to infect my body cells, I've taken away its ability to do that. So now I've got these antigens from my polio virus floating through my body. My B cells bind to those antigens and then make memory cells, then make plasma cells against it, make a whole bunch of antibodies, and those antibodies float around in my body. And then when I get a real polio virus in me, then they cling to the outside of the virus and prevent it from being able to bind to my body tissues and cause polio to happen. We also do that with exotoxins. So a really good example of that is the tetanus toxin. Why do we get a tetanus shot? Is not against the tetanus organism, but instead we surround the tetanus toxoid so that it can't go to our neuromuscular junction and cause tetanus to happen. Okay, so here's just a picture of that happening. Here's the antigen and antibody binding. So here's neutralization. So like it says, masks the dangerous parts of the bacterial exotoxins or viruses. Here's agglutination and precipitation. So when agglutination and precipitation happen, then that enhances phagocytosis. Here's the activation of complement, which can then lead to either cell lysis or enhancing both phagocytosis and inflammation. Okay, whew. Antibodies come in 5 groups. We can remember MADGE, M-A-D-G-E, for the different types of antibodies that we have. So here they go. So let's say that let's use the same polio vaccine. So polio, we're going to make at least these 2 groups against polio. And then we're going to have IgDs against polio. The IgEs are funky, and we'll get into that when we get into allergies. And then IgAs are more of a general function of things that could come to us through our mucous membranes in our skin. Well, everything comes to us through our mucous membranes and epidermis, but I'll talk about their specific role in a minute. Okay, so let's do the IgMs first. Okay, so no, let's do the A's. Let's do the A's first, because they're the ones that are going to see it first in our bodies. So out there in our body secretions, in our sweat, saliva, and tears, we're going to have this dimer of antibodies. They're going to stick together at their tails, at their stem regions, and they're going to poke out, and they're going to be secreted in our external environment. And we can get in our milk too, intestinal juice, whatever we're secreting. And so what we try to do is stop the pathogens from actually binding in the first place. Okay, so they're just going to be out there in our body secretions and helping prevent the antigens from getting into us in the first place. But now they get into us, and now we find the B cell that's going to fight against the Staph aureus, for example. So we have a skin infection, Staph aureus skin infection. Okay, so what's going to notice that? Well, the B cells are going to have IgD on their surface. And IgD is that Y that sticks out as a receptor for the B cell. IgDs are never secretory. These guys are never found free floating out in our body. They will always be on the surface of the B cell as a receptor. Okay. Then that's going to trigger, once these have bound to an antigen, then that's going to trigger the B cells to produce IgMs. And so what the IgMs will do, they form a 5 antibody molecule, and I'll show you a picture of that in a minute, which is released. It's the first one released by the plasma cells during an infection. And so because it has 10 binding sites on it, because each antibody has 2 arms, so it can bind to 10 red blood cells at a time. So when it does bind to the red blood cells, then we get agglutination. and then the macrophages can find it more easily. Okay, we can also, IgMs can also, because they're the first ones that we start secreting, can activate complement as well. Then after we have been infected for a while, for a little while, days, then our IgMs will, our B cells will stop, or our plasma cells will start producing IgMs, and will start producing IgGs of the same specificity, but now they just changed their class, and they become the most abundant circulating antibodies. These are the ones that cross the placenta and give your baby that immunity for the first couple of months of life. They also will activate complement, but they're the ones that are going to be out there fighting against bacteria, viruses, and toxins. Okay, so with that primary response and then our secondary response. So here is what they look like. Here's the IgM, first immunoglobulin class secreted by plasma cells during primary response. We can tell if we have IgMs, you know, how current our infection is. Fixes and activates complement, and then the pentamer is what goes around in our blood plasma and binds to, you know, if we get the wrong blood type. And notice it says numerous antigen binding sites make it a potent agglutinating agent. Okay, IgA is a dimer, so the tails are stuck together. Secretory, found in our body secretions, stop pathogens from attaching to epithelial surfaces. IgD is found on the cell surface of the B cells, function as the antigen receptor, and IgMs can as well. IgGs, most abundant antibody, secondary and late primary responses, fixes and activates complement, and you can look at that. And then IgEs. Okay, so IgEs are the ones that are involved in allergies, and their stems are attached to mast cells or basophils, and both of those are the cells that have histamine granules within them. So when we degranulate and the histamine comes out, then we get an allergic reaction. So mediate inflammation, which is good. Mast cells out in our skin are what are producing that inflammatory response, but sometimes these guys get a little screwy and they get overactive. And if you think about where do we have allergic responses, okay, because they're going to be secreted by our plasma cells in our skin, and we get hives, and we get rashes, and mucosa of our gastrointestinal tract, we get celiac disease. Respiratory tracts, we get asthma. Tonsils, still, you know, inflammation in our pharynx. Respiratory tract, upper respiratory tract, like our nasal cavity, that's when we get our allergies of our runny nose and stuff. And so levels rise during severe allergic attacks or chronic parasitic infections of the gastrointestinal tract. You know, I'm not sure why, besides inflammation, why we make allergies are weird things. I don't really quite understand our purpose in having an allergy, but anyway, there we go. Okay, now active and passive humoral immunity. So there's 4 ways that we can develop humoral immunity. Let's show you this picture because this is a lot better. Okay, so humoral immunity then is either active or passive. Active immunity means that we've been presented with the antigen and we mount an immune response, or passive means we've been given the antibody from somewhere else. Now, within each one of those, we have naturally acquired and artificially acquired. Naturally acquired means we got it ourselves through normal means. Artificially acquired means we were injected with it. So in the most common humoral immunity, which is naturally acquired active, we come in contact with the pathogen, we get infected, we mount an immune response, and we get better. Okay, so, and then we have memory, and then we remember that for the rest of our lives. Naturally acquired active. Artificially acquired active, on the other hand, we're going to get shot with the antigen again in a vaccine or an immunization. So we get dead or attenuated pathogens. You know, I don't think we even use attenuated anymore. Our recombinant vaccines are so good now that attenuated means that it could still, there's still pieces there that could cause an infection, and that's why We used to have an attenuated poliovirus, which is on the sugar cube, and we just ate it. And then that's how it was introduced instead of getting a shot. Well, we found out that that attenuated may have caused some people to come down with an infection. And so we don't even use it anymore. We just use the shot polio vaccine. We don't use the oral polio vaccine anymore. But artificially acquired, we're going to get the antigen that's not going to cause disease, and then we're going to go ahead and mount an immune response against that, and then have immunological memory. All right, passive immunity does not give us immunological memory because we never get to make antibodies ourselves. Instead, we're given the antibodies. So in naturally acquired passive immunity, the antibodies from our mom will cross the placenta, may be present in our breast milk, but even if you don't breastfeed, your baby is still receives the antibodies because they cross the placenta. So the antibodies that she's made in her lifetime will be given to her baby because in the first 3 months of life, baby immune systems just don't work and they need to power up. And so it takes a while. It takes 3 months for them to start powering up. And so in the meantime, the mommy's antibodies hopefully will provide some kind of immunity. That's why it's really important not to take your brand new baby out and see the world for, as long as possible, really. And do not let people kiss your baby and breathe all over your baby and everything, because babies are just not designed to fight off infections, specific immunity. So protect your little ones, and it's okay to just say, you know what, let's wait on you seeing my baby. You'll get to see my baby. Here's some pictures. Look at my Instagram. But please be careful with your newborns. Okay, so that's naturally acquired passive, and the only person you can get naturally acquired passive immunity from is your biological mother, nobody else. And then artificially acquired passive is when we are given what's known as a gamma globulin shot, or notice it says an exogenous antibody that was made outside of our bodies by somebody else, rabbit, I don't know. Something else was infected with the agent. So let's take hepatitis, for example. Human hepatitis, a rabbit can't come down with human hepatitis. So we inject hepatitis A into the rabbit, and then we take out the hepatitis A antibodies that it makes. Now, let's say that you are eating at Taco Bell, or you are eating strawberries. This is a real example. You're eating strawberries in school lunch. Well, if the strawberries hadn't been washed properly, and strawberries are quite notorious for transmitting hepatitis A because it's a oral fecal route transmission. So if human fecal waste gets into the irrigation water of strawberries, chances are there's going to be a hepatitis A virus on your strawberry. And so little kids, so here's what happened when I was living in California. So little kids at this elementary school were given strawberries in the school lunch, and then all these little kids came down with hepatitis because of the hepatitis infection. Now, we don't want to run the risk of that hepatitis A virus infecting you at all. So what are we going to do? It's too late to go through maybe the course of vaccinations. So we're going to give you the antibodies that we harvested from that rabbit. So we're going to give you a gamma globulin shot. Now, some of you may be return missionaries. Return missionaries also can get gamma globulin shots against diseases and encephalitis and probably yellow fever and other things where they're not vaccinating you against it, but we are vaccinating, we're not vaccinating at all. We are giving you the antibodies so that you can keep them in case you're infected with that organism. We call them peanut butter shots because they're proteins and they're really thick and gooey, and it takes a long time to shoot into you. I have not had a gamma globulin shot. If you've had a RhoGAM shot, or you're familiar with the RhoGAM for mommies that are Rh negative, it's a gamma globulin as well. So that the antibodies have been produced by another organism, and then we shoot those antibodies into you. Again, not giving you active immunity or memory, I mean. It's just passive. We're just trying to hold off you getting infected by those preformed antibodies. Okay, I'm going to stop right here and do a different video on cell-mediated immunity because I think your brains are full for this one.